Venn diagrams, probably not something we need to review much because you've been using them through middle school and high school and probably into college in different areas, and so not a big deal. But sets of objects are often represented by geometric figures known as Venn diagrams. They're created by John Venn, an Englishman who lived from 1834 to 1923. In a Venn diagram, each set, because this is how it comes up because it's sort of about sets, represented by a closed or bounded figure, such as a circle or a rectangle. If the statements P and Q have a conditional statement, if P and then Q are represented by sets of objects, respectively, then the law of detachment must be justified by a geometric argument. So, like for example, an Venn diagram is used to represent that statement, if P then Q, it is absolutely necessary that P lies within Q. So we can see here that if I am in P, then I'm also going to be in Q. So versus the other way around, I could have Q, but it not necessarily imply P. All right, here's a couple examples. So if a player plays, we already looked at this before, I apologize. If this is a perfect example, let's go on the next slide and see if I have a visual of that. Nope. I'm going to pause for 1 second. All right, there's the visual I was looking for. So they go through and they identify and they say that A are people who are talented athletes. And so basically this whole outside circle are all talented athletes. But then we come in and we say that B is a Rockville High School basketball varsity player. And then we say that if a basketball player B, then they're talented. So that means that B is within A. So we can see that we use point T to represent Todd. So Todd is somebody that is a high school basketball player at this particular school. So therefore they fall into the category of A, meaning that they are a talented athlete. The statement if P then Q is sometimes expressed as all P are Q. Doesn't happen very often, but it just depends on the way it's worded to you so that you're familiar with this idea. So that'd be something to write down, is that conditional statements if P then Q could be written as all P are Q. For example, the conditional statement of examples 8 and 11 can be written all Rockville High School basketball players are talented athletes. So it's just a conversation, right? So we look at it both ways, because if they're at this school, they are talented. So that means all high school basketball players at this high school are talented. The compound statements known as conjunctions and disjunctions can also be related to intersections and unions. Relationships can be illustrated by the use of Venn diagrams. So conversation for the next couple of slides are intersections and unions. So a couple things to pinpoint here when we're looking at intersections and unions is this idea of symbolism. So an intersection is going to be P, and then you get this upside down U and Q. An intersection is also worded as and. So you can see that down below. So it's P and Q. So this literally reads P and Q. So to be an intersection, it's just like it sounds, it's got to be in both. So this is not in the intersection. This is not in the intersection. So just kind of keeping that in mind. The only way it's in the intersection is if it's in both. It's more unique. Whereas a union is saying you can be in one or the other or in the intersection. And so this comes along, remember, with the word or. And we see that that's down here. That's interesting. That's a typo. I apologize, okay? That should say, my bad. No, that's right. This is just reading out. The elements are in P and Q or both the form of union. So this is the union. I'm sorry. Oh my God. Whoo, deep breath. Union is definitely going to be or. So that should say P or Q. Okay. So I apologize about that. So it's in one, it could be in the other, or it could be in any or of the two. All right, and that looks like it wraps it up for us for Venn diagrams. All right, so those are our videos for section 1.1. Thanks.